So this topic here, this new topic is going to be on phase changes. So the first phase change I want you guys to realize is a liquid going to a gas. Okay. A liquid going to a gas is called evaporation. That's just a liquid going from a liquid phase to a gas phase is called evaporation. Okay, going back. Okay, going backwards, a gas to a liquid is called condensation. Okay, so these are two words I'd like for you to know. Okay, one is evaporation, liquid going to a gas. The other one is condensation, which is the reverse, a gas going to a liquid. So with this liquid going to a gas, there is something called, and a gas going to a liquid, both processes. There's something that I want to teach you called vapor pressure. Okay, vapor pressure. So let me try to define vapor pressure here. Vapor pressure, first of all, is a back and forth. So this back and forth, liquid to gas, gas to liquid. I'm going to call it a dynamic equilibrium. Okay, we're going to go back and forth. It's a dynamic equilibrium that's going to go back and forth, okay, between liquid to a gas and a gas to a liquid. Secondly, it's a pressure, okay? Okay, that a vapor or a gas exerts. Right, so which means it's going to have units of pressure. Okay, what are those units of pressure? Okay, you remember this from Chem 1. Okay, we can have units of pressure, millimeter of mercury, atmosphere. Okay, all these units of pressure. It's a pressure because it's a gas exerting or sitting on a liquid, and it gives a pressure. Okay, so that is vapor pressure. The pressure the vapor exerts, or the pressure the gas exerts. Let's write that down. Okay, it's a pressure that the gas exerts on the liquid. I want another thing here. This is going to be a common theme in this course. I want everyone to recognize. Well, there are many things I'm going to teach you, okay? But one of the things that's going to be common, it's going to be almost, you'll see this over and over again. And vapor pressure is one of them, and that is it is quoted at a specific temperature. Okay? Vapor pressure is quoted at a specific temperature. So you change the temperature, you change the vapor pressure. Reduce the temperature, the vapor pressure of water is a different number. You increase the temperature, the vapor pressure of water is a different number, or any type of liquid. Okay, any type of liquid to gas. Okay, that's one of many things that you'll learn that is going to be very specific at a specific temperature. So that's what I mean, quoted at a specific temperature. Change the temperature, you change the vapor pressure. So let me try to explain this to you. So let me see if I can be successful in explaining to you guys this concept of vapor pressure. Okay. So imagine you have two beakers here. Okay. So one beaker, okay, is a beaker full of water. Okay. Okay, this is my water molecule. Okay, water is H2O. Right? Okay, totally separate beaker. I'll fill it up with propane. Okay, we'll call propane, you know propane, right? Propane, it's an alkane. Okay, we'll have it as blue. Okay, this is propane. So that is propane. Propane is CH3, CH2, CH3. Okay, so here we have water in one beaker, and a separate beaker we have propane. Okay, two separate beakers. One beaker has water, a separate beaker has propane in it. Okay, so vapor pressure. Okay, so what is vapor pressure? Let's just focus our attention on this water molecule. Okay, everyone focus on this. Focus on that one. Okay, so what is vapor pressure? This vapor pressure is where this liquid breaks free. Okay, what do I mean by break free? Okay, when I say just focus on this one, it breaks free and it evaporates. It breaks free, it evaporates. It just evaporates. When it breaks free and it evaporates, it's now a gas. It's now a vapor. Okay, what can that vapor do? Remember, vapor pressure is a dynamic equilibrium. So what can it do? It can go back and condense. Condense. Okay, I'll say condense, C-O-N-D. Condense. So here we have this back and forth going, right? Okay, so you guys with me? Okay, so one molecule will evaporate, and just as it evaporates, another thing it can do, it could condense, and when it condenses, it exerts a vapor pressure, because this is a back and forth affair. So we have a back and forth. It condenses, it evaporates, right? It evaporates. What happens when it evaporates? It can exert a vapor pressure when it condenses. Once it condenses back into the liquid, it can vapor pressure, correct. Okay, it can exert a vapor pressure. Right, same thing with this one. Okay, same thing with this beaker of propane. Okay. So look at one molecule of propane. It can break free. What do I mean by breaking free? It will evaporate. It evaporates. Okay, what can happen when it evaporates? What can it also do? It evaporates and becomes a liquid. What can it do? It evaporates and becomes a vapor. Then what it can do? Very good. It can condense. Zendaya. Right? It can. Is it J or a Z? Jen, Z. Okay, I'm thinking Z. J. So it is right here. I think on Canvas it has you with a Z. They messed up. Zendaya. So she is right. Okay, back to the lecture. When it evaporates, okay, become a vapor, it can condense. When it condenses back down, that's when it exerts a vapor pressure. Okay. Again, okay, we have a back and forth affair because it's a dynamic equilibrium. Okay, evaporate, condense. Once it condenses, it exerts a vapor pressure. Once it condenses, goes back into the liquid, it exerts a vapor pressure. Right? With that being said, which do you think has the higher vapor pressure? Zendaya, let me pick on you for a minute. Okay. What would you, if you were to guess, which one would have the higher vapor pressure? Okay. That is correct. This would have the higher vapor pressure. Okay, very good. Okay, why is that? Why did you pick this right answer? What was your reasoning?
Because it's propane, it's like CH3
Yeah, that's true, but what's the reasoning? You're right, but what is this held together by?
Hydrogen bond.
Which one is held together by hydrogen bonds?
Oh, wait, never mind. Is it dispersion?
This is held together by dispersion, okay? Okay, what do we know about dispersion, Layla? Is it a weak force or a strong force? Weak or strong? Okay, it's weak. Okay, it's weak. Okay, so would it be, if it's something is held together by dispersion forces, would it be easier to evaporate or harder to evaporate? It should be easier to evaporate. Because it's easier to evaporate, it will also be easier to condense. That is why this has the higher vapor pressure. Okay, what about water? What is water held together by? What is the main intermolecular force for water? This is the one where you want to say hydrogen bonds. Is that a strong or a weak force? Okay, in this context, it's a strong force. Because it's a strong force, would it be harder or easier to evaporate? Harder to evaporate. Harder to evaporate means it will be harder to condense. Harder to condense means harder to evaporate, harder to condense, less vapor pressure. You see, less molecules will evaporate. Why will less molecules evaporate? Okay, why will less molecules evaporate? Okay, because of the hydrogen bonding that holds one water molecule with another water molecule with another water molecule with another water molecule, so on and so forth. Why is this easier to evaporate? Dispersion. Dispersion is weak. It's easier to evaporate because a propane is held together with another propane with dispersion. Another dispersion and dispersion, which just goes out like this. Okay, if you take propane and put it on a surface, by tomorrow it will be gone. Okay, because it evaporates. If you ever work with barbecue fluid or work with any of these types of fuels, okay, they will evaporate. Put them on the surface. And what will happen in a couple of hours or the next day? What will happen? It will evaporate. It will evaporate. Okay, because it's just dispersion forces holding these together. So you guys are correct. Very good. This has a higher vapor pressure, but the explanation, make sure you say dispersion. Okay? Hydrogen bonding is for water. Right, so that is the idea behind dispersion. And that is the idea behind hydrogen bonding. They all relate to vapor pressure. Okay, this all comes down to vapor pressure, which has the highest vapor pressure, which has the lowest vapor pressure. So vapor pressure. Right, there's another topic, another term with regards to vapor pressure. And that is delta H vaporization. Delta H vap, or delta H vaporization. Right, what is delta H vaporization? Okay, it's an energy. Okay, it's an energy. How much you have to put in. Okay, how much you have to put in to vaporize 1 mole of a substance. Okay, how much? 1 mole. 1 mole. It's an energy you put in to get something to vaporize. Okay, it's the energy you have to put in to get something to vaporize. We call that delta H vap or delta H vaporization. So we have some values here. Okay, so before I talk further, the units of this are kilojoules per mole or joules per mole. How much you have to put in to get 1 mole. Okay, 1 mole. 1 mole to get that to go from a liquid, 1 mole of a liquid to 1 mole of a gas. How much energy you have to put in? How much energy is the input you have to put in? Okay, units are per mole, kilojoules per mole, or joules per mole. Right. So let me ask you this question, okay? If you have a stronger intermolecular force, okay, like a hydrogen bond, do you think your delta H vaporization value will be higher or lower? Okay. It's held together like water, okay, held together with hydrogen bonds. Would that delta H vaporization be higher or lower? The amount of energy you need to put in to vaporize. Huh? Very good. It will be higher. Okay. Higher. Nicholas. Higher. Okay, so. Okay, so just want you to know. Okay, if you're held together by strong intermolecular forces, it takes more energy to vaporize it. Okay, where's all of that energy going? It's going up to break that intermolecular force, hydrogen bonding or ionic or whatever. Okay, so the higher the delta H vaporization, okay, this means the stronger the intermolecular force. That must be overcome to get something to vaporize, correct? That must be overcome to get something to vaporize. So this higher, this delta H vap, this delta H vaporization, this means the stronger the intermolecular force within the molecule. Okay? Because all of that heat energy or all of that energy is going to break up the force. Okay. Look at water here. Okay, water has a boiling point of 100 degrees C. Right? Water has a boiling point of 100 degrees C. And look at the delta H vaporization. Okay? 40.79. Okay, where do you think all that 40,790 joules per mole, okay, kilojoules per mole, joules per mole, okay, where's all of that going? Okay, where's all of that heat going? Okay. It's going to disrupt the hydrogen bond, okay, within water. 40,000 joules of energy, or 40 kilojoules of energy, just to break 1 mole of water, just to vaporize 1 mole of water. Okay. And all that energy is going exerted to disrupt the hydrogen bond. Okay. What do you think about ethanol? Okay, 39,000 joules over mole. Hydrogen bond, okay? Okay, why do you think methane is so low, 9.2? Because it's dispersion. So 9,000 joules or 9.2 kilojoules to boil methane. Okay, very low. It's dispersion is the primary intermolecular force. Okay, what about diethyl ether? Remember the ethers? Okay, what do you think the 26? Where's that going towards? 26,000 joules or 26 kilojoules. Okay, what is that being used to break? Ethers. What are ethers held together by? They're polar. Okay, polar. Okay, so it's a little bit less than the hydrogen bonding one. So the delta H vap, delta H vaporization. All right, here is the graph of vapor pressure. If we plot vapor pressure on the y-axis temperature T on the x-axis, it's going to look like this. Okay, this is the profile. Okay, for any substance, any liquid, it's going to have this, I don't know what you describe this shape, but it's going to look like this. Okay, so this is something I want you guys to know. Okay, if your vapor pressure at the y-axis is 1 atmosphere, okay, if it's 1 atmosphere, and you okay, you hit that line on the curve. Sorry about that. Okay, so the vapor pressure on the y-axis, temperature on the x-axis. Okay, the shape, the profile is going to look like this. It's going to have that shape. Okay, you see that over here. Okay. So I just want you to know this, okay? Your vapor pressure is on the y-axis, correct? Okay, at 1 atmosphere, okay? If 1 atmosphere, you push that, you get that all the way to this curve, okay? And you go all the way down to temperature. Okay. At 1 atmosphere, vapor pressure, at this curve, vapor pressure over T temperature, we call that the normal boiling point. Okay, normal. You know this term? Normal. Okay, normal boiling point. So for, let's say this is water. Okay, what would the normal boiling point of water be? 100 degrees C. Okay, just as life experience tells you. Okay, this just is the boiling point when your vapor pressure is one atmosphere. 1 atmosphere. Okay, so whenever you see the word normal in chemistry, or if you take higher level chemistry class, normal means the pressure is 1 atm. That's just the vocabulary they use. So this is the shape of the graph. Vapor pressure on the y-axis, temperature on the x-axis. At 1 atmosphere, we call that normal boiling point. For water, it's 100 degrees. For some other things, it's a different number, different boiling point. Okay, so normal means what? Normal means 1 atmosphere. Okay. And this is, what does the shape look like? If you plot vapor pressure on the y-axis, temperature on the x-axis, what will it look like? Okay, it will look like this. Okay, it's going to look like that. That's the shape of the curve. Okay. All right, so let's move on here. All right, this equation is something I will give you on the exam, and there'll be a problem on the test utilizing this equation. I'll give you this equation. On the test, you'll just have to know how to solve this. All right. So let's just take a brief 5-minute break. I'll go to my office, get my calculator. Meanwhile, you guys could take a little break, and we'll resume at around 10 o'clock or so.